Hello, everyone. This is joint work with Alice Sinclair. So in the random closed model, the random closed model establishes probability distributions over the subgraph of a graph G. And there are two parameters, an edge probability P and a cluster weight Q. And each subgraph of the form BA, where A is a subset of the edges of the graph, receives a weight. And the weight is given by this expression here, where you have a P factor for each edge in the configuration, a 1 minus P factor for each edge that is not in the configuration, and then a Q factor for each connected component. So here C of A is the number of connected components of the induced subgraph BA. So here's an example. The graph here is C4, and the weight it receives is given by this term here, where, for example, you have one edge, so you have one factor of P. There are three connected components, so you have Q to the 3, and so on. So this is an important model because essentially it unifies the study of several other models that are important that we care about. So, for example, if you see here, if you take Q equals 1, the model reduces to a standard bond percolation model, where every edge is sampled independently with probability P to obtain a subgraph of G. And in particular, if the graph G is a complete graph, then this is the Edwards-Rengi random graph GMP model. Okay? Moreover, when Q is an integer, this model is dual in a precise sense to the ferromagnetic Ising and Potts model. And just to be slightly more precise, what I mean by dual is that there is a probabilistic coupling of the random closed measure and the ferromagnetic Ising-Potts measure, such that we can map correlations in the spin world to path in the edge world, and we can use this connection to prove interesting stuff about the about the spin systems. In addition, you can see that if we take, for example, Q smaller than 1, then we favor configurations that do not have many components. So in particular, if Q goes to 0, the set of limits that arise for various choices of P include other interesting distribution over the subgraph of G. For example, we can choose P such that the random closed measure converges to the uniform measures over the spanning trees, or the spanning forest, or over the connected subgraph of G. Okay? Again, in this model, it makes sense to talk about the measure in the infinite graph. And here is an alternative definition, although we can define it in the same way as is what defined in the previous talk. We can consider a sequence of graphs that converges to some infinite graph G. And then the random cluster measure in this infinite graph is just the limiting measure of this sequence of measures on each of these graphs. So here is an example. Suppose that we consider the random cluster model in a box, a square box, in the integer lattice graph. Then if we take the limit on the side of the box, as n goes to infinity, n is the side of the box. If we take n to go to infinity, the limiting graph is going to be the infinite integer lattice graph, and this is the way we define the random cluster measure in the infinite lattice graph. So again, here we have the question of when this limit is unique, but that will not be the focus of this talk. So an important feature of the model is that there is a phase transition, or it is conjectured that there is this phase transition. So we have a critical value of the model parameter P, such that with high probability, if P is smaller than this critical point, all components are finite. And as soon as P is larger than this critical point, then there is at least one infinite component. For example, if we go back to C2, this critical value is none. It was recently shown by Befar and Dominic Kubin that it corresponds to the self-dual point. But in general, we only partially understand the phase transition, and we only understand in some classes of graph. In the finite setting, we can roughly think that this phase transition corresponds to the emergence of the giant component, just like in the GMP case. Okay. So the focus of this talk and the focus of my work is to understand the behavior of Markov chains on random cluster configurations. So these are Markov chains that the state space are all the random configurations of a given graph G, and the stationary distribution of this microchain is going to be the random cluster measure. Okay? And in particular, we're interested in understanding the mixing time of this microchain. Since I'm one of the first talks, I'm going to just say what it is. It's just the number of steps the chain has to take until it's close to the stationary measure, assuming that you start from the worst possible starting configuration. Okay? So, well, by now we know that there is a well-established connection between phase transition and the behavior of microchains. For example, we know of many phase transition that changes substantially the mixing time of some microchains. But on the other hand, in many other models, we have been using, for many years now, we have been using mixing times of various microchains to understand the phase structure of these models. So there is a two-way connection here. In addition, well, we know that fast mixing microchains provide algorithms for sampling from the stationary measure. And in particular, the random cluster dynamics is also interesting because it's closely related to the spin systems, but the techniques from a spin system seems to fail in the random cluster setting, essentially because these techniques use the locality of the spin world, and the random cluster model is a highly non-local model because connectivity is a global property of the graph. Okay, so this is one of the microchains that we are interested in. It's the standard heat bath microchain, which is a global dynamics. And the way it goes is as follows. You have some random cluster configuration A, and we pick an edge uniformly at random from the graph. And the edge gets added with this probability here. And this probability is essentially the probability that the edge is in the configuration if we condition on A minus C. And otherwise, the edge is removed. So this is a dynamics that is defined in many models and have been studied in many models. So this expression, in the case of the random cluster model, has this nice expression here where we have it is equal to P if E is a co-edge, and we say that an edge is a co-edge if it doesn't change the number of connected components of the graph by adding or removing the edge. And otherwise, it's given by this expression. So here is an example. Here you have some random cluster configuration in the 6x6 grid. You pick a random edge, say that one. That one is a bridge. It's a co-edge because it changes the number of connected components, saying that so it gets added with this probability. So then we pick this one. This one is in a cycle, so it's not a co-edge, so it gets removed with probability 1 minus P. So the other dynamics that I'm going to be telling you about in this talk is the change master microchain. And it goes as follows. We have a random cluster configuration A, and in the first step, we go component by component, and we activate each connected component independently with probability 1 over Q. Right? Then we will add each active edge independently with probability B, otherwise we will remove it. Okay? Let me, well, before I show you an example, I just want to say that it is straightforward to check that this converges to the random cluster measure, and that, as you can see from this step here, is only well defined when Q is greater or equal than 1, because otherwise this probability is greater than 1.
Does active edge, you mean an edge that joins two vertices in the same component, or does the edge have to be present?
No, an active edge is an edge that both endpoints were active. It doesn't have to be in the same component. If it is in the same component, it is active, but it can be from different components too. So here is an example. Again, we have the 6x6 grid. In the first step, every component gets activated independently with probability 1 over Q. So here are the orange ones are the ones that got activated. We forget the configuration in that region, in the active region, and we resample every edge with probability B. So we had found a new configuration there, and then this is one step of the change master microchain. Okay, so as well now, it's easy to see that there is a substantial difference between the two dynamics I just described. The heat bath is a local process that changes one edge at a time, while the CN dynamics is a global process that changes many edges. And in spin systems, it is known that some of these global microchains are faster than their local counterpart. In fact, substantially faster in some regimes. But our first theorem here shows that this is not the case in the random cluster model. Here we show that It's a comparison inequality between the mixing time of the heat bath and the shake master. And it shows that if we ever show that if we have an upper bound for the mixing time of the global microchain, then we get an upper bound for the heat bath, and the same for the lower bound. And we only pay polynomial factors in this. So we showed this by generalizing a comparison technique of Ulrich. So I won't tell you much about the proof of this.
Is it for any graph, or is it got to be constant degree?
Any graph. Okay. Any graph. This is for the comparing in the random closed setting. If you go to spin systems, then you have this restriction with the degrees.
So if you did Swenson-Wang, then Ulrich is wrong?
No. If it is a Swenson-1, this falls. But if you want to compare a Swenson-1 with the heat bath in the spin systems, then you pay the degree.
Oh, okay.
Yeah. Okay, so the talk is going to have two parts. In the first part, in the first part, I will tell you about some results on the shake mass and mixing time on the Meanfield, and in the second part, I will tell you about some results on the mixing time for the heat bath dynamics in situ.
Just a quick question. Does the comparison estimate also work? There is this generalization of Chase-Mekta where instead of having activating or not activating, you give each cluster a color between one and an integer color between 1 and a floor of Q, and then you resample within each color set. Right?
You're asking if the comparison holds in that case? So the comparison was actually proved for that case by Ulrich, and what we did was...
I thought he just proved it for K equals Q, where Q is integer. He just
for an integer. So he proved this...
K minus 3. No, I'll choose two colors. I'll choose two colors, and each cluster will get, with probability 1 over Q, it will be red, with probability 1 over Q, it will be blue, and otherwise it's inactive. And now you resample inside the blue and inside the...
Oh.
You can also consider this in the paper towards the end, and they claim that it's supposed to be fastest if you choose the largest possible number of colors. Which is
yes,
probably your techniques will work, right?
Yeah, I'm not sure if it will hold there, but the point is that the whole comparison inequality holds in a more general setting than what was proved in the Ulrich setting. So what I put here is just a special case of the generalization that we're able to prove. So maybe it holds also in that setting. I'll have to check. Yeah. Okay, so in the first part, as I said, I'm going to talk about the Meanfield, and the Meanfield is a case where G is the complete graph, and this is a useful non-trivial starting point. In most, with the statistical physics motivation, we usually start here, then we go to random graph, and ultimately we want to understand what is going on in high-dimensional lattice. So in the first transition here, we reparameterize P as lambda over n, and there is a critical value of lambda that is given by this expression here. And we know that if lambda is smaller than lambda critical, then all components, the largest component we have size log n. And as soon as lambda is larger than lambda critical, the largest component is going to be of linear size, and it's going to be zeta rn, and zeta r is, we know what it is, and it's a function of lambda and q. Okay. So then this is work by Bolwach, Griemen, Jansson, and Lushak for a few years back. There has been some work on the mixing time of microchains in the Meanfield, but most of this previous work has been for the Swenson-1 dynamics, which is a similar dynamic to CM dynamics, but it's only defined for integer Q. For example, for Q equals 2, we fully understand the mixing time of the Swenson-1 dynamics, and this is work by Cooper et al. And Long et al. And until recently, we only had partial results for the integer Q greater or equal than 3 regime, and this was work by Goran Jerum and Hover. But in an independent work 2 hours, we now have the full picture of the mixing time for the Swenson-1 for integer Q greater or equal than 3, and you will hear more about this tomorrow. But the point that I want to make is that the Swenson-1 is not a very natural dynamics for the random closed model because it's only defined for integer Q. It uses the connection with the spin system, while the random closed model it makes sense for every real value of Q. Okay, so this is our first result concerning the mixing time, and it's essentially a complete analysis of the mixing time. So when when Q is between 1 and 2, we show that the mixing time is of the CM dynamics is zeta log n for all non-critical values of lambda. Now, when Q is greater than 2, the behavior is more interesting. We show that there is a regime around the critical point where the dynamics is essentially exponentially slow. And as soon as lambda is not in that window, then the mixing times become very fast. It's actually zeta log n. And there is also this interesting behavior in one of the boundary points where we have a power law for the mixing time.
In the first case, when the root n should be n, right?
Root n should be n, yeah. In fact, this is still in my to-do list, but it should be n here, and I will tell you also in the open problems what is going on with this critical point.
Does some amazing thing happen at lambda r as well? Is it not known?
Oh, well, lambda r is also special. I mean, in the sense that the analysis is different, but it has the same log n mixing time. Okay, so now I'll give you some interpretation of the results, why we have this change in behavior when Q goes from 1 to 2. And it goes down to the continuity of the phase transition. So when Q is between 1 and 2, we know that there is this second order phase transition, which means that the phase transition is continuous or very smooth. And if here the x-axis is the size of the largest component, here we have probability. We see that in the subcritical we have only one mode around zeta log n, in the supercritical around zeta rn, and even in the critical regime we also have only one mode. So it's a very smooth phase transition. But as soon as Q is greater than 2, the phase transition becomes discontinuous. So in the critical point, we'll have two modes for the size of the largest cluster that each one accounts for roughly half of the probability mass, right? So this is the phenomena called phase coexistence. But when in a short neighborhood around, in close neighborhood around this critical point, we see that these two modes are still present in a form of a second log maximum of this probability mass. And the states that are here are the so-called metastable states that are states that trap the Markov chain. So if you start the Markov chain from there, the Markov chain cannot leave that state in polynomial number of steps. And this is why we can show that the mixing time between lambda L and lambda R is also, it is exponential. Okay, so just to give you a flavor about the proof.
Sorry, can you return to that slide? What is the picture on the right there?
So,
the top.
this one?
Right. What is?
So this picture is saying that the size of the largest cluster is concentrated around has a linear size, and it's well concentrated around this point.
So what is the difference between those three? It's just where the mean is?
Where the mean is. Yeah, sorry. Yeah, so here, where the mean is, this is... yeah. Okay.
Equals 2 and lambda equals lambda c.
Yes. Yes, the behavior is much more complicated, exactly at the Q equals 2 case. Yeah. So we will show to bound the mixing time. We use the coupling technique. We essentially will start the Markov chain. We start from two arbitrary. We will analyze two copies of the Markov chain starting from arbitrary initial configurations, and we know that if at some time t the probability that the chain is not coupled is bounded by some constant, then this is a bound for the mixing time. This time provides a bound for the mixing time. So our coupling will have two main phases. In the first phase, we will run the chains independently until the size of the largest component in each chain has roughly the right size. And in the second phase, then we're going to couple the evolution, but now starting from two configurations that have the right largest component size. Okay. So here is an overview of the first phase, and here the key observation is that I'll draw a picture here. So you have some random cluster configuration. So these are the components. And in the first step, I activate a fraction of the components. That I activate these ones here. and I'll forget, so this is the CM step. In the CM step, then I forget about the edge configuration, and I resample every edge with probability P here. So essentially what I'm doing is I'm replacing a fraction of the graph with a GMP random graph, or a GAT P random graph in one step. And now we can use this to analyze the evolution of the microchain. For example, in the phase 1A, we can show that after log n steps, there is going to be a most one large component. And this is because we know that a GMP random graph, even if it is subcritical or supercritical, it will have a most one. So it's easy to see how, if you have many, they will cancel in a few steps of the dynamics. Okay. The most interesting phase is phase 1B, where now we have this large cluster, and we want to analyze how the change of this cluster changes as the dynamics progresses. And if we use here using L of xt for the largest cluster, it's easy to show that when L of xt is inactive, this percolation step is going to be a subcritical step. So all the new components that are created are of size log n with very high probability. So the largest component will not change. But if L of xt is active, then the number of active components is given by this, where you have zeta tn, which is the size of the largest component, and then you have a cube fraction of the remaining vertices. And the new largest component is going to be the largest component of a GMP random graph. So this will give us a drift function for the size of the largest component that I wrote here. So it's here by this expression. And now we look at how this function looks, and we see that between 1 and 2, the function looks like this, where if lambda is in the subcritical regime, the drift is always negative, and this makes sense because if you're in the subcritical regime and you have a large component, you want to destroy the large component. But if lambda is in the supercritical regime, it has 1, 0, and the 0 corresponds to the expected value of the largest component. If it is smaller than the expected value, we see that it is positive, and this is what we want. And if it is larger, the drift is negative, so it's always converging to this expected value. Okay, so everything is nice here. So the critical point corresponds to this curve here the first time it has a 0. Okay, but when we go to the q greater than 2 case, the drift function looks quite differently. When lambda is smaller than lambda L, well, again, this is always negative, and this is in the subcritical, so this is good. When lambda is larger than lambda R, we again have the same behavior. We have the 0 here corresponding to expected value. But this behavior does not go all the way to the critical point. This curve here corresponds to a lambda L and lambda R drift. And if lambda is actually, for the values of lambda between lambda L and lambda R, the curve will have 2 zeros instead of none or 1. What this means is that, for instance, in the subcritical case, this portion of the curve here is positive. So this means that you are in the subcritical case, you in the stationary distribution, you are not likely to have a large component, but here, on expectation, you are going to increase the size of the component. So essentially, this is what we are able to use to show that the mixing time is slow between lambda L and lambda R. So here are the two special points. The curve corresponded to the two extreme points, lambda L and lambda R, and we see that the main issue here is that there are these 2 zeros here, and the drift essentially becomes 0 in these points. So we have to do something different because we have negligible drift. And in fact, what we're able to use is there is actually enough variance to push you out of this interval. Okay, so now that was about phase 1. In phase 2 is when we actually do the coupling of the microchain, but now we can assume that the two largest components have roughly the same size. Here, the key step is going to be to couple the activation of the components in a way that roughly the same number. Well, exactly what we want is that exactly the same number of vertices are active in each copy, because if we are able to activate the same number of vertices in both copies, then we can put an arbitrary bijection between the edges and use this bijection to resample all the edges and get the same component structure in the active subgraph. So you can imagine now that if you have the same component of structure in the active subgraph, all you need to do is to cover the whole configuration, and then you will achieve two subgraphs with the same component structure. after you achieve two subgraphs with the same component structure, there is another coupling argument, but this is a simpler argument that takes you from two configurations with the same component structure to two configurations that are the same. But the key in this phase 2 is how to couple the activation to ensure that with some probability the two configurations have exactly the number of active vertices, the same number of active vertices. So this is how it is done. So suppose that these are two copies of the Markov chain. We will couple the activation of the two giant components together. And after that, we will create a mashing between all the components with the restriction that first we will ignore the isolated vertices. And the other restriction that we put is that we only match components of equal size. Right? Now, and then after we put that maximum matching here in A, and we use that maximum matching to activate to activate the component. So here, after doing the activation with the matching, we don't create any difference between the two copies. So we have the same number of active vertices in both. Then we do the activation in the giant component, but from phase 1, we know that the difference between the two is small. So there is some discrepancy that is created here, but it's not too large. And indeed, we put the remaining components here. We do it independently, and this again creates more discrepancy. But the point is that since all these components are small, the discrepancy is also not too large. So overall, you can create a discrepancy that is of order root n with constant probability. And then you observe that the isolated vertices, the number of active isolated vertices is a binomial random variable. So you do a coupling of the binomials here, and try to use this coupling to fix whatever discrepancy was created from the previous activation. So you can, I've hidden some details here, but this is essentially what is going on. Okay, and that's it for the first, the 2/3 of the talk. So in the last part, so now if you zoom out, you can come back now, because this is a fairly different argument where we analyze the heap bath, the local Markov chain in situ. Okay? So remember that the heap bath is this Markov chain. Well, we're looking at the finite boxes of the interior lattice graph, and we pick a random edge, and the edge gets added with this probability. Okay? So there is some previous work, and this was done by this result of Ulrich. This is a more general result, but when applied to the heap bath in situ, we get this polynomial bound of n to the 6 log square, and this will hold for all interior values of Q and all non-critical values of P. So this result has some drawbacks. Well, first, it only holds for interior Q. The bounds it produces are not very strong, so they are weak polynomial bounds. And also the proof goes through a comparison argument, which is indirect, so it fails to show any kind of connection with the phase transition. Our result for the heap bath is a type bound for the mixing time of n squared log n for all Q greater or equal than 1 and all non-critical values of P.
N is the side length?
N is the side length, so it's proportional to number of edges or vertices and vertices. Yeah. So before giving you a flavor of the proof, I have to introduce a few notions, and one of them is this idea of boundary conditions. And the idea is that sometimes we want to understand the random closed measure in the box conditional on some configuration in the complement of the box. So this configuration in the complement will create will induce some connectivities in the boundaries, and we will use a partition of the vertices in the boundary to encode this connectivity. So a boundary condition is a partition of the boundary vertices. Here is an example. These three vertices here are connected through the exterior, so they are in the same element of the partition, and so on. Okay. So here are a few more examples. These are the two extremal cases where all the vertices are wire. So this is called the wire boundary condition, or this is the free boundary conditions. There are two boundary conditions here. And there is a special class of boundary conditions that will be important for us that we call the size homogeneous boundary condition. And we define these boundary conditions as follows. We say essentially that there is only one non-trivial element in the partition. So you only have one connected component, one non-trivial connected component in the boundary. And in addition, the boundary condition is homogeneous across each side. So if two vertices are wired in one side, then the whole side has to be wired. So all of these here are side homogeneous. These two are side homogeneous. This one is not, because we have three non-trivial elements in the partition, and this one is not because it is not homogeneous on this side or in this side. Okay. So the other notion that I have to introduce is this idea of spatial mixing, which is slightly different for the random cluster. Well, it's slightly different for the random cluster mode. So here the idea is that we look at an edge E, and we consider a box of radius r around this edge. And we would like to measure the influence of the configuration in the complement of this box on the state of the edge E. And for that, what we do is we look at this difference in the probability that the edge is occupied, conditioned on two different configurations on the complement. Now, if this difference decays exponentially with the size of the box, and this holds for every edge, then we say that spatial mixing holds for the random cluster mode. So spatial mixing is closely related to the notion of exponential decay of connectivities, this is a property for the infinite measure. And Befar and Dominic Copin showed that in the infinite lattice we have exponential decay of connectivity. The probability that U and B are connected decays exponentially with distance throughout the subcritical regime. In previous work, Alexander had shown that if exponential decay of connectivity ever hold in the infinite lattice, then it would also hold in the finite volume for arbitrary boundary conditions. And then he uses this exponential decay of connectivity to show that spatial mixing holds for a restricted class of boundary conditions and for integer Q. What we're able to do first is to use this machinery developed by Alexander here to show that the spatial mixing holds for size homogeneous boundary condition for all subcritical values of P and for all Q greater or equal than 1. So here let me give you an idea of why spatial mixing is susceptible to the boundary conditions, because this is substantially different to the spin systems. So first suppose that you have this edge here and the box does not touch the boundary of the outer box. The influence from the complement can only go to E in the form of path. And by exponential decay of connectivity, we know that this path decays, the probability of this path decays exponentially with R. And this can be turned into a rigorous argument. But when the edge is close to the boundary, influence does not only comes from from the boundary of the box. It doesn't only come from the configuration. It also comes from the boundary condition of the outer box. So if the boundary condition is something like this, something arbitrary like this, you can take influence from very far regions from E to close to E using the boundary condition. Yeah.
Boundary, so it means that if I modify one site, then the marginal on a site that's distance r from it is exponentially, the difference is exponentially small in the distance.
So what I meant,
Usually we say we
You didn't say strong.
Oh, just spatial mixing.
Yeah, so I've been careful of not using strong or weak because the notions are not mapped. I don't think they are mapped in the same way to the spin systems. So what I mean is that if depending on the kind of boundary conditions that you have in L in the bigger box, then you could have or you may not have a spatial mixing in the whole box. And it's this effect here that because boundary conditions can actually connect these kind of vertices like this, you can take influence from far regions to regions close to it just using the boundary condition of the outer box. But the point is that size homogeneous boundary conditions avoid this phenomena. We did this property that there is only one non-trivial connected component, wire component in the outer boundary, avoid this issue. Okay, so now here is the proof sketch, our proof sketch for our main result for the heat bath. We show that a spatial mixing implies a fast mixing. We actually show that the mixing time is at most n squared log n log n squared. And then we show this boosting lemma that says that if you show that the mixing time is at most n to the 2 plus epsilon for sufficiently small epsilon, then this can be boosted to the right n squared log n bound. Since we know that lemma 1 In lemma 1, we have a spatial mixing for all non-critical values, all subcritical values of p and q greater than 1. Then we have that the mixing time in this regime is n squared log n. Now, then we use the self-duality of the model to show that if you have some bound of m in the subcritical regime, then this can be turned into a bound of order m for the supercritical regime. And finally, we prove that the mixing time is lower bounded by this, which shows that our upper bounds are tight. Okay, so in lemma 2, we show that the spatial mixing implies fast mixings, and this is a notion that has been around for a while in spin systems. This work where it showed that some notion of decay of correlation implies fast mixing, and I only put here the ones that where we borrow some inspiration for our work, but there are many more. And again, we're going to use a coupling, but in this case, we're going to use a specific coupling. We're going to use the identity coupling. And in the identity coupling, we pick the same random edge in both copies, and then we use the same random number to decide whether to add or remove the edge. The identity coupling is a monotone coupling, which means that it's at time t, yt is a subset of xt, then this property is preserved by the steps of this coupling. And one consequence of this is that it is sufficient to consider as the starting states the two extremal configurations, the one that has no edges or the one that has all the edges. Okay, so our goal is going to be to bound the probability that xt is not equal to yt. And for that, we can, by union bound, we can try to get a very good bound on the probability that xt and yt disagree in each edge. And to bound this probability, we will consider two additional processes, ct minus and ct plus. Ct minus will start from the empty configuration, just like the y copy, and ct plus will start from the complete configuration, just like the x0 copy. And the four copies are going to be coupled with the identity coupling. The only difference is that zeta d minus and zeta plus are going to ignore the updates outside some box of radius r around the edge e. So after t steps, we see that zeta d has not performed any updates here, zeta d minus has not performed any updates here, and the same for zeta d plus. And in addition, by monotonicity, we see that zeta d minus is a subset of yt, is a subset of xt, and so on. So by monotonicity, instead of bounding this probability, we can bound the probability that ct minus and ct plus disagree in the HE. So here is the intuition of how to do that. We look at the stationary measure of these two processes, and we see that is a random closed measure in this smaller box with some boundary condition, in this case the free, and in this case the wire one. So after sufficiently large t, we know that zeta d minus is going to be close to the zeta d minus and zeta d plus are going to be close to the stationary distribution. But in addition, by spatial mixing, if we choose the size of the box sufficiently large, we see that the probability that these two stationary measures disagree in the edge decays exponentially with the size of the box. So you can imagine that if zeta d minus is close to this one and zeta d plus is close to this one, then the probability that they disagree also decays exponentially with the size of the box. This follows from a triangular inequality. But the main question is how large should we pick t such that ct and ct minus and ct plus are close to their stationary measures. And here is where the second property of psi-homogeneous boundary condition becomes very relevant again. So the point is that if we look at the boundary condition in these smaller boxes, the boundary condition in these smaller boxes is always psi-homogeneous. So this is clearly the case if the box doesn't touch the boundary, because it's either the wire or the free. But even if the box touches the boundary, since the boundary condition in the outer box is size-homogeneous, the boundary condition in the inner box is size-homogeneous. So this gives us some kind of recurrence. And in fact, if we are provided with some bound on the mixing time as a function of the length of the side length of the box, we can get a bound on this t by essentially noting that after f0 log n steps, the ct minus process will have mixed in this inner box. We go a little bit further to actually get very close to a stationary measure. And then we have this slowdown factor here because this is essentially a lazy Glower dynamics where only with probability log square volume over n squared the edge is updated. So we have this slowdown factor. So from a guarantee on the mixing time, we obtain a new, stronger guarantee. So for example, if we start from a very trivial upper bound of e to the n squared, after 4 iterations of this idea, you get that the mixing time is n squared log n squared. I think a few minutes left. So finally, in lemma 3, I won't tell you much about this, but it is a boosting lemma, where if we start from a bound on the mixing time of 2 plus epsilon, which n to the 2 plus epsilon, which we already have from the previous result, then we can boost it to the right answer. And the idea is that instead of establishing a recurrence for the mixing time, we establish a recurrence for this quantity here. And the main new ingredient to establish this recurrence is to bound the speed at which disagreements propagate. And this is also a standard notion in a spin system, but that have to be modified to a random closed setting. What we are able to show, okay, let me tell you what I mean by the speed of propagation of disagreements. So suppose that you have 2 configurations that agree in some box around an edge E. So they have the same configuration inside this box, but then they disagree outside. We want to measure how many steps of the heat bath dynamic we need to actually propagate those disagreements to the center of the box. And what we're able to show is that we're able to provide a bound on the speed of this propagation. Essentially, if the probability that x and y at time k n squared differ at E is bounded by this expression here, provided k is smaller than r to the 1/4, r is the radius of the box. So this is how we adapt the notion of propagation of disagreements to the random closed setting. So now this is zooming in into this smaller box BER. What we do is we consider this maximal region that isolates the edge E from the boundary of the box. So in this case, it looks something like this. It doesn't touch the boundary. The point is that the 2 configurations, we know that they are always going to vary in this kind of regions. So we're going to consider a sequence of these regions. And if we update some edge inside this region, the region is not modified. If we update an edge that is very far from this region, the region is also not modified. But if we pick an edge that is exactly in the boundary, then this can be problematic. So what we do is, we do something simple. We just take the whole component out of the region. Again, this xt and yt are always going to vary in this region. The key observation is that since we choose yt to be from the stationary measure, and we know we have this exponential decay of connectivity property, so all the components are small, we actually need many updates to reach the center of the box. And if we don't, and this is an unlikely event if we don't take too many steps of the microchain. Okay, so for open problems, so for the Meanfield, from the comparison inequality that we just showed, we get some bounds on the mixing time that are roughly n to the 4. We think that the right answer is n to the n squared, but we don't have a good way of analyzing this. In situ, the main open problem is the analysis of this critical point. And here is no so bold conjecture that the mixing time should be polynomial for q smaller or equal than 4 and exponential for q greater than 4. And this is based on a conjecture about the continuity of the phase transition that is widely believed.
So
and
at q equals 2 is known or something, right?
At q equals 2 is known for the easy mode. Yeah. Yeah, but that's the heat bath for the easy mode. It's not known for the q equals 2 for the random closet, but something is known for the understanding of the q equals 2 case is much better.
Okay.
And then there has been this recent development regarding the continuity of the phase transition, so there is some hope on at least getting some partial results for the mixing time at the critical point. And beyond this, we would like to understand random closed dynamics in general graph and the 0-1 regime. Questions?
Does these techniques for Z2 somehow extend to so-called non-amenable graphs like graphs that would do not grow to path?
You mean amenable?
Amenable, yeah.
Well, yes, we know that in a spin system, these techniques hold in more general settings. But we don't have a spatial mixing for the random cluster in more general settings. So that would be the starting point. But we also think that this spatial mixing probably holds in more generality. But we'll have to start there.
Any other questions? Okay, let's thank the speaker again.